Okay, now we reach the last session, session 3, under the topic of creational design patterns. We are going to discuss builder, prototype, and singleton design patterns. These design patterns are easier to understand compared to the previous abstract factory and factory method design patterns. For the builder, we are going to discuss about we are going to see the code generator example. For the prototype, the character cloning example, and then singleton event manager example. Okay, we start with the builder design patterns. So for the builder design patterns, the aim is to provide the same construction process that we can create the different presentations. The construction process is the same. So in this, the structure of this pattern consists of director. So the director will give the command, step by step command. It will use the command in the abstract builder. So the abstract builder will be implemented in terms of interface or abstract class. So in this case, it's interface. And then we have a concrete builder that will give the instruction. The sequence of instruction will be the same, even though for different concrete builder. And then the concrete builder will generate the product. Okay? So the spirit is, or the main point here is to allow user to use the same step but with different implementation. This is the example that we're going to discuss, where we are going to generate the code from the specification here. So as an input for the code generator, so in the code generator object, we'll have the same step: open and read file, find message name, attribute operation, generate language specific code, and then a close file. And then different code generator will produce the different implementation or the code programming language. Okay, so this is the diagram that represents the builder design patterns for our example. We have code generator, that's run or execute, all step by step build step by step construction process that's provided by message builder. And then message builder is an interface class, so it is implemented in the either CPP builder or Java builder. Okay? So both CPP builder and Java builder will use the same steps but with different implementation. CPP builder will produce the C++ source code, and Java message builder will produce the Java source code. And then this both concrete object will interact with the generated product. So this is where the code is stored or generated. So string here inside this class. Okay, so how's about the code? First, we see the message builder class. The message builder class is here. Okay? So for the message builder class, we have the same steps to use to create the product in target language. So for the message builder, we will provide the same step. So that the code generator can call the same step no matter what is the concrete class is, or whether you want to generate in what the different programming language. Okay, if you see here, this is the CPP message builder as an example, where the CPP builder will generate the codes, the C++ code. So this is a step in the code, then generate to add code, and then have a class name, and then generate the attributes, generate the operations here, and then finally close the class. So this is generated code. So final version of generated code is here. That is done by CPP builder by implementing all the steps. So this is the steps that defined in the message builder class and then implemented in the CPP message builder. So for Java message builder also will done with the same with the CPP message builder. So now we have seen the code of a message builder, CPP builder, and we can guess about what is happening in the Java builder. Now we want to see the code generator and then also the generated product. So this is the code generator. For the code generator, it will call, associate the message builder. The message builder, P builder, this one is interface. So at this point of time, when you see the code, you don't know about whether the P builder is belong to CPP builder or Java builder, because it will be supplied during runtime. So during compile time, we cannot see. So that's why this code is stable, and then we don't have to change the code here. It's all the same creational process is used for all target languages. So it will comply with the open for extension and close for modification. Okay, so this is the summary of using the builder design patterns. So we first the steps. First, we identify and design the product class, the generated product, and then identify the product's creational process and algorithm. And then you're using knowledge acquired in step 1 and 2, design the builder interface. That's have a steps, common steps, and then identify and design classes have a different presentation. For example, in this case, for CPP or Java message. In future, maybe C# or Python. So it is we can call it is we can assume that this is extendable. So it is maintainable, towards maintainable software. So the builder provide the following benefits: separate objects construction process from its representation, as you see from the example, where irrelevant of whatever the presentation, can separate the construction process and then change to existing representation without modifying the code. And then finally provide the final control over the construction process of object created at discrete point of time. So which differ from abstract factory design patterns. Okay? I think it is easier to understand compared to the abstract factory pattern. Okay, next, prototype design pattern. This is also very simple to understand because the main purpose is actually to specify the objects by copying the property of another object. So we want to create the runtime object without we don't want to duplicate the prototype object at runtime. So we duplicate the object. So here we have the client operation here that don't know about anything about the object, but you can clone any object for the concrete prototype A or from concrete prototype B. Okay, so this is an example. That's fictional example again in computer games. So consider an enemy component for a gaming system. We have an enemy. So the detailed design of the enemy component includes a wide variety of enemy specification defined for the game. So we have different profiles, weapons, etc. So the game designer have identified the need for each character, provide the methods creating copies of themselves during the game. So a character clone can be made with identical energy level, weapon profile, etc. So this functionality is required to develop an enemy registry of different character and create and add enemies at any point of time. For example, you shoot one enemy and then it come appear about 10 enemies more. So they use a clone. They clone the power, everything. So I'm not what we call now at my age. I didn't play video game, computer game anymore. But for you, I think this example is very familiar. Okay. Okay. Now we try to solve the problem that we described earlier. So in this case, we want to create the new or the clone the enemy at a certain place at a certain point of time in our game application. So here we have a class character, and then we can put the method to create copies of terrestrial character, and then this one for the aerial character. Okay? So we can add the methods that implement the character interface. So we have a return new aerial character, and then we refer to this to copy the current object. Okay. However, if let's say we need to add the new character, for example, aquatic character. Now we can add here duplicate terrestrial and then also duplicate aerial But the problem is when we want to add the aerial character, for example. And so we have to modify this code. That means we violate the open-close principle. So now we try to apply the prototype design pattern so that we do not violate the OCP. So we have a game engine here. So this one will instantiate this interface character, and then we'll have a uniform command. So the game engine, we don't have to modify the code there. So and then add the prototype. This one, add the prototype clone interface method to the character interface for this clone method. So we have a special clone method. We are not interested on the attack method in this example. So the clone method is implemented in both terrestrial enemy and aerial enemy character. So it is easier if we want, for example, this is the aerial character here. So we just add the implementation of this code class to we implement that interface. So this is the new code where we have this is implemented terrestrial enemy character and aerial enemy character that implements the above interface class. So we have a character clone here. The clone will return the character, return new aerial enemy character, and return enemy terrestrial enemy character. So we have done with the character and the different type of enemy character implementation. Okay, so now we want to replace this in the game engine. So we don't want to do this because it is violates the OCP. Okay? So we don't want to use this code. And then we replace with this. So we have a character energy registry, max number of enemies. This is the array of energy registry. And then here we random location to get the next enemy location that we want to locate. And then we clone. When we do the clone, and then it will return to the enemy character, about the enemy registry for the next enemy character. So that is the prototype pattern. It makes us easier to create the duplicate the object the current state in the program. So as a summary here, how to the steps in design the prototype design pattern. We identify and design the common interface that needs duplication. What is a common interface? In this case, we have a character, and then the needs duplication is a different type of concrete object. So identify the design concrete product. For example, in this case is a aerial and the terrestrial and aerial character. So if you want to put aquatic character and letter, so it's easy. So for each concrete product, create step to implement the code clone methods that particular concrete object. So this is very simple step, and then for the simple implementation of the prototype. So the benefit is client are shielded from knowing the internal structure of objects. So the client don't, the game engine in this case, don't know about what is the objects, whether it is terrestrial or aquatic character. Reduce number of classes instead of having two classes for creator and product classes. Okay, so now we move to the last one that we are going to discuss under the topic of creational design patterns. It is a singleton design patterns. So this is very easy because singleton, the purpose of singleton is to provide the one and only one instance. Only have one instance of a class. For example, you need the counter, the class to count each connection to the website. So you cannot create the new class because you want to increase the counter with the same class. So it is easy to use. Private constructor restrict the object installation. So the constructor here control the constructor of a singleton will control that one and only one instance method. Instance is created. It will return the same instance. So this is the example here. So consider application that requires event logging. So to log event, the application consists of many different objects that generate events to keep track of the action, status, operation, etc. So the decision is to create an event manager that can be accessed by all objects and the same instance of event manager to be accessed by all other objects and used to manage all events in the system. So even in instantiation, the event manager creates an event list that gets updated as events log. So at specific point during the software system's operation, these events are written to file. So to prevent conflicts, it's desirable that to give a at any given time it's only one instance of the event manager executing. So we try to see how to implement the singleton class. Okay, so for the implementation of the singleton design pattern, if you see, this is the most important method, the get instance. So if you see here, the get instance event manager, it will return only one and only one instance. If there is no instance defined yet, so it will create the new event manager and then return new event manager. Is if let's say the instance is not equal to 0, that means it's already there. So the get instance or log get instance and then log event, for the log event can be done straight away to the get instance. That means the instance that's given by this method. If that means that this methods again control whether the to control that one and only one instance is created. So that's all for the singleton design patterns. So again, the steps to design the singleton, we have a set the visibility of the constructor to private, and then define the private static member attributes to get the one and only one instance, and then create the public static get instance method to control the construction of the object. So to make sure that only one object is instantiated. So benefits of singleton design patterns: it provide control access class to a single instance of given type, and then reduce the namespace since it provide alternative to global variables. This one is actually the similar concept that we use during C programming or C++ programming. Before this, we use the global variables. So it can be customized to permit the variable number of instances. That's maybe 2 or 3 instances. Okay, so with that, we end the discussion on the creational design patterns.